Good morning. I'm Michelle Catteray-Bradley, a Reference and Research Specialist in the Science, Technology, and Business Division of the Library of Congress. I'd like to welcome you to today's program on the James Webb Space Telescope, in which we'll learn about a new space-based telescope with improved technologies and expanded capabilities. The James Webb Space Telescope, or JWST, is an international collaboration of NASA, the European Space Agency, and the Canadian Space Agency. The instrument will work primarily in the infrared range of the electromagnetic spectrum, with some capability in the visible range. It will be the premier observatory of the next decade. It will be used by thousands of astronomers worldwide to study every phase in the history of our universe, ranging from its first luminous glows after the Big Bang to the formation of solar systems capable of supporting life, and the evolution of our own solar system. The telescope will have a mirror 6.5 meters in diameter, eclipsing that of the Hubble, which was 2.4 meters, and it will have a sun shield the size of a tennis court. The project is working toward a 2018 launch date, and the JWST will reside in an orbit about 1.5 million kilometers, 1 million miles from the Earth. This program is the second in a series of programs in 2012 and is presented through a collaboration now in its 6th year between the library's Science, Technology, and Business Division and the NASA Goddard Space Flight Center. Our speaker today is Dr. Amber Straughn, a research astrophysicist in the Observational Cosmology Laboratory at NASA's Goddard Space Flight Center in Greenbelt, Maryland. Dr. Straughn serves as the Deputy Project Scientist for the James Webb Space Telescope Education and Public Outreach. Her research focuses on interacting and star-forming galaxies in the context of galaxy assembly, and she has most recently been working on infrared spectroscopic data from the new Wide Field Camera 3 on the Hubble Space Telescope. Her broad research interests include galaxy formation and evolution, galaxy mergers and interactions, star formation and black hole growth, and dark energy and its effect on the galaxy merger rate. Dr. Straughn has a BS in physics from the University of Arkansas in Fayetteville, and both an MS and a PhD in physics from Arizona State University. She has been with NASA at the Goddard Space Flight Center since 2008. NASA has graciously provided literature and handouts on this and other research which are in the lobby. If you are interested, please stop by and pick up some. Also provided for viewing are materials on telescopes and their history from the Library of Congress collections. Please join me in welcoming Dr. Amber Straughn.
Thanks very much, and welcome to all of you today. I want to start off today by talking to you a little bit about Hubble. So you all are probably familiar with Hubble, but more than talking to you about Hubble, I want to tell you the story of Hubble. Because the Hubble story is a human story, and it's a story that you're all part of, whether you know it or not. So Hubble Space Telescope, the conception of it first began in the early 1900s. And it's named after Edwin Hubble, who was an astronomer back then who made a very crucial discovery about the universe. Using the Hooker telescope in California, he discovered that the universe was expanding. So in the plot here on the bottom left, what he saw was that the most distant galaxies were receding away from us at the fastest rate. And so because of that, you can deduce that the universe is expanding. A very crucial discovery that was first made by Edwin Hubble in the early 1900s. So just a few years later, the people started first thinking about putting a telescope in space. And this was one of the pioneers of modern rocketry, Hermann Oberth. So we first started having these thoughts in the early 1900s, and it was about 40 years later before these thoughts started to become more of a reality. The astronomer Lyman Spitzer first convinced other astronomers in 1969 that putting a telescope in space was a good idea. And so he gathered the support of the national academies, and in 1969 put forth a publication that suggested that we put a telescope into space. And of course, in this city, we all know that we have to get Congress to approve funding for these sorts of things. And so that happened in 1977. And shortly later, we started building the telescope and the Space Telescope Science Institute up in Baltimore that ran it. So 1990, Hubble Space Telescope is launched on the Space Shuttle Discovery. And it was deployed just a few days later. And you might recognize the commander of that shuttle mission that launched Hubble. That was Charlie Bolden, our current NASA administrator. And then just a few months after the launch of Hubble, it was discovered that Hubble had a flaw in its mirror. So the size and shape of Hubble's mirror was off by just a tiny, tiny amount. But it was enough to make the images not what we expected. But Hubble was so important, we decided to go fix it. And so a few years later, we basically we launched another telescope and basically put a contact lens on Hubble. So that mission was the first servicing mission, or SM-1, and that happened in 1993. And so what previously we saw with Hubble, which was a more blurry image than we expected, with the new optics, the details of the galaxies came through. So that was the first servicing mission. The second servicing mission happened a few years later in 1997, and astronauts went up and replaced a couple of the instruments, replaced some of the batteries, the gyroscopes, the things on the telescope that make the telescope function. And then later on in 1999, we were already planning the third servicing mission, but one of the last gyroscope failed. And so we had to basically turn off Hubble. So because that happened, we decided to kind of speed up that next servicing mission. That servicing basically broke it into two parts. And so that first servicing mission 3A, happened sooner than expected. So we went up on the shuttle again, late 1999, and did some of the work that we had planned for that servicing mission. And then a few years later, we kind of did the second half, so servicing mission 3B. So during that servicing mission was when we put in the famous Advanced Camera for Surveys that's produced a lot of the beautiful images that you're probably familiar with from Hubble. So that was servicing mission 3. Servicing mission 4 happened in 2009, and as you all probably know, that was the last servicing mission to Hubble. And we had a couple of new instruments that went up on that mission, including the Wide Field Camera 3, which I had the opportunity to work on, which was really exciting. And so because of that, I got to go down to Florida and see the shuttle launch, which was amazing. So I want to show you some pictures from that shuttle launch. And most of these are not pictures that I took, but they're beautiful nonetheless. So this is actually a historic picture in NASA's history because, as you'll notice, there are two shuttles on the launch pads there. That's never happened before. So some of you who might know a little bit about NASA's history might know that this shuttle mission, this last servicing mission to Hubble, was canceled after the Columbia disaster. But astronomers and the public worldwide kind of fought to get this servicing mission back so we could go back to Hubble. And NASA finally agreed to that, to have this last servicing mission. But one of the things we had to do in order to go forward with that mission was we had to have a rescue shuttle ready. And so for the first time in NASA's history, we have two shuttles completely prepared and ready to go into orbit in case something happened to the first shuttle on ascent. So if you remember the Columbia disaster, what had happened was some of the tiles on the underside of the shuttle had been damaged on ascent. And so if that same thing were to happen again, we wanted to have a rescue shuttle ready to go. So that's why there are two shuttles on the launch pad here. So just a few of the amazing photographs that have come out of this particular mission. You know, I'm an astronomer, I'm a scientist, so the science part of what NASA does is really close to my heart. But the human exploration, nobody can deny, is such a wonderful part of NASA and of our country's history in general. I'll just show a few more photos here. So this is from inside the shuttle, and you can see the two windows here. Those are actually Hubble's solar panels. So the shuttle's approaching Hubble and about to grab it so we can work on it. And that's Hubble. That's it, out in space. Here's an astronaut getting ready to install one of the instruments. And this was taken from Earth. This was actually taken by an amateur astronomer. And so what this is the disk of the sun had a fraction of a second to snap this picture. And what you see up in the upper left there is the shuttle and Hubble, both orbiting at the same time. So I love this image. Yeah, it shows you a sense of how small we are. And so here is the image of the astronaut installing the Wide Field Camera 3, which was the instrument that I worked on and have now since worked on data from this instrument. So this is a very special image to me in my research. So amazing things our astronauts have done to get these kinds of things going. All right, so I couldn't give a talk about Hubble and about JWST without showing you some Hubble images, so I'm going to scan through a few of them. Of course, Hubble's done a lot in the solar system, image of Jupiter, of Saturn. And in our own Milky Way, this is still fairly close, we know that stars are formed inside nebulae. So these large regions of gas and dust, very famous Eagle Nebula, pillars of creation, we know that stars are formed inside clouds of dust like this. Another image of stellar creation. And then later on, after stars have evolved a little bit, their winds shed out the dust and gas around them, and then they kind of shine forth. And so this is an example of a young star-forming region where the stars have kind of blown away that outer dust. You can still see a lot of it around, but the stars inside have started to shine through. Another example of that. And then at the end of their lives, stars sometimes do amazing things. Depending on their mass, they can end their lives in supernovae. And so this is an example of an exploding star at the end of their lives that's shedding its outer layers out into the surrounding universe. This is the very famous Crab Nebula, and it's also an example of a stellar death. So this is what stars go through at the very end of their lives. And this is also a really good way to show our human connection to the universe. All of the elements in the universe, besides the very light elements, helium, hydrogen, are formed inside stars. So the elements in your body, the very iron in your blood, was created inside of a star that ended its life like this. Here's a picture of the middle of our Milky Way galaxy towards the center of the Milky Way. This is actually a composite image of Hubble and the infrared Spitzer telescope and the X-ray Chandra's telescope, all three NASA telescopes. This is an example of a star cluster, globular cluster, near the edge of our Milky Way galaxy. But this is an image, one of the first images that Wide Field Camera 3 took. And so this just gives a great example of the wide variety of colors that we see in stars in our universe. Another example of stars. And then outside of our own galaxy, of course, there are other galaxies. In fact, we know that there are about 100 billion other galaxies, each with 100 billion stars. And so this is this is our nearest big neighbor, Andromeda. So it's very similar to the Milky Way in a lot of ways in its structure. It's quite a bit bigger than our Milky Way, but we know it has a huge black hole lurking at its center, just like our Milky Way does. Another face-on spiral galaxy. This is an elliptical galaxy, which are the largest galaxies in the universe. So this galaxy, what just looks like a big glowing ball of gas, all of that glow is stars. And then the thing at the center is an active black hole, and you can see a jet shooting out to the side. This is an example of a starburst galaxy. So all kinds of variety of galaxies in our universe. This is another nearby galaxy, a large spiral that's interacting with a satellite galaxy. Galaxy interactions are actually quite common in our universe. This is the antenna galaxies. So these are two galaxies that have undergone a huge galactic collision. This is another example of a galactic collision. This is called the Mice. Two galaxies that have come close enough to become gravitationally interactive and have started to merge. Another example of two galaxies that are interacting, you can see how the bottom one has pulled out the spiral arm and started to pull it down closer to itself. This is a great example of how stars form in between galaxies. So the gas inside these galaxies, again, these galaxies have undergone an interaction and have caused stars to form, what would seem like in the middle of nowhere. These are more galaxies that have undergone interactions. When we see things like this big ring here in this upper right galaxy that's offset from its center, that's a good clue that it's undergone an interaction recently. Another famous picture, this is called Stephan's quintet. 5 galaxies that look close. Actually, the one in the upper left, the more blue galaxy, is a little bit more close to us. This is an example of a galactic city. So this is a galaxy cluster, which is the most dense regions of our universe are often in galaxy clusters. So many galaxies kind of sit off by themselves, but this is a place where many galaxies are kind of packed in very tightly in a relatively small space. And one of the really interesting things we can study in galaxy clusters like this is what's a phenomenon called gravitational lensing. So the galaxies, the mass in this huge galaxy cluster serves to act as a physical lens for objects behind it. So if you're here, we have the galaxy cluster here, and we have background galaxies. From our vantage point, the mass in this huge galaxy cluster is bending and magnifying the light of the background galaxies. So this big pink stretched out thing on the right side, this is a great example. I'm going to zoom in on that. So you see how this beautiful spiral galaxy that's back behind that cluster has been stretched and lensed and magnified by the intervening mass of that galaxy cluster. And we know that galaxy clusters themselves, the whole things often merge. So this is an example of 2 galaxy clusters merging. All of the white-yellow light you see is from Hubble. The pinkish and bluish is representation from Chandra. It's X-ray light, and this is good evidence of dark energy right here that we're seeing, because we know that these 2 galaxies are colliding, and we know there's more mass there than what we can see. So of all these beautiful images that Hubble's given us, if I had to pick my personal favorite, it would probably be this one. This is the Hubble Ultra Deep Field. This is the deepest picture of the universe that Hubble has ever taken. So Hubble stared at one tiny patch of sky for 11 days. This is like looking at the universe through a straw. If you held out your pinky finger, you could cover up this tiny patch of sky. And yet in this tiny little piece of sky, Hubble sees 10,000 galaxies. So absolutely amazing what Hubble has seen in these images. I've done a lot of my personal research in this part of the sky, and it's amazing what you can see here. So many galaxies, so much diversity in the galaxies. They're all different shapes and colors and sizes. There's a lot we can learn from these images. So telescopes, in a sense, are like time machines, right? Because light takes a finite time to travel. And so when we look at things that are distant from us, we're seeing them as they were in the past. And right now with Hubble, we've done a good job of seeing pretty far back in the past. But those most distant things that we've seen are very tiny. We can't see much about them. We can't learn much about them. And we are completely missing that very first epoch of galaxy formation. And so that's what JWST is going to see. We know the universe is about 13.7 billion years old. With JWST, we're going to be able to push back all the way to when those first galaxies formed and see those first galaxies form. And I'll talk about that in a little bit more of the science soon. And then just last year, of course, you all probably know the Nobel Prize in Physics was awarded for the discovery of dark energy. And Hubble had a very crucial role to play in that discovery as well. So that's Hubble. A very brief summary of all the amazing things that Hubble has done. And I just want to point out that this is your telescope. If you're a taxpayer here in the US, in a very real sense, this is your telescope. All the data, all of these images I've shown you, all the data that Hubble has ever taken is free and available for you to download. Hubble itself every year has a call for proposals where astronomers around the world propose their great ideas to observe with Hubble. And anyone in the world can write a proposal to observe with Hubble. So it really is a community telescope. But as you all know, Hubble's been in orbit now for over 20 years. We've gone back to service it 5 times, the most recently in 2009, and it's working great. It's basically a brand new telescope after that servicing. But the shuttle era is over. We can't go back with the shuttle, and so we've had to start thinking about what comes after Hubble. So that's what I want to tell you about next.
construction is the premier telescope of the next decade. A next-generation space telescope designed to cause yet another giant leap forward in our understanding of the cosmos. It will carry some of the most advanced technologies ever placed on an orbiting observatory.
"18 articulated mirror segments, 2.75 times the diameter of Hubble's primary mirror. Microshutters, wavefront sensing and control subsystem, 12 by 18 meter, 5-layer Kapton-based sunshield."
The Webb Telescope, a revolutionary tool able to study every phase in the history of our universe.
The Webb Telescope.
So that's it. That's what's next. All right, I want to tell you a little bit now about the Webb Telescope. And following a little bit on what I've told you about Hubble, the Webb is the scientific successor to Hubble. So we're building it to answer these big science questions that Hubble can't answer. In many ways, we've pushed Hubble to its limits. We have learned so much from it, obviously. The Hubble has completely revolutionized our understanding of the universe. But again, there are some things that it can't do, and so that's why we have to build these new observatories to answer those questions. So there are kind of three primary differences between Hubble and Webb that I want to talk to you about. The first one is the size. Webb is big. Hubble is about the size of a school bus. The Webb is more the size of a jet plane. Okay, and so Northrop Grumman, who is our prime contractor for the telescope, has built this full-scale model that it takes around to show people and teach people about the telescope. This is actually up at Goddard. So this is a full-scale model. It's the same size as the real thing, but of course is just steel and plastic. But you can start to see how big the telescope really is. And we need a big telescope to answer these big science questions. So Hubble's mirror is about 2.4 meters across. The Webb mirror is about 6.5 meters across. So all told, it has about 7 times the light collecting area. And of course, the size of a mirror of a telescope is one of the most important parts, right? Because the mirror collects light. The size of the mirror also determines how sharp of an image you can get. And so we really need the big mirror in order to see some of the details of the science things that we want to do. So again, the mirror is 7 times bigger than Hubble, 6 to 7 times. And when you consider the size of the mirror, the wavelength range in which it will operate, and the efficiency of the detectors, the new technology that we're using, Webb will be something like 100 times more powerful than Hubble. So the second key difference between Hubble and Webb is that Webb is an infrared telescope. So Hubble sees the universe mainly in optical light, visible light that your eyes see. Webb will see the universe in a little bit of visible light, red visible light, and then infrared, so light that's redder than your eyes see. And this is completely driven by the science. All the big science questions that we have right now demand an infrared telescope in space. So that's why we're building it this way. And then the third big difference between Hubble and Webb is its location in space and its temperature. So Hubble orbits the Earth about 350 miles up. Webb will orbit the Sun along with the Earth about 1 million miles away. So that's about 4 times further away than the Moon. And the reason we have to put it into deep space is so that it will be very cold. So again, infrared, or it will be an infrared telescope. An infrared light is a lot like heat radiation. So in order to see these faint infrared signals from the distant universe, the telescope itself, the detectors, the mirrors, everything about the telescope has to be very, very cold. And so we're putting it out into deep space so that it can get very cold. Now NASA currently has several telescopes out in that part of space, so we know how to get there. That's not a problem. But we need it there to be very too. So we will, since the telescope is so big, it's actually too big to fit on any rocket fully deployed. And so we have to build this telescope so that we can fold it up to fit inside the rocket fairing. And then it will deploy once it is launched into orbit. So here's a sequence showing how the deployment happens once it's in space. So the first things that pop out are the solar panels, and then the things that are now unfolding are sun shields. So again, it's an infrared telescope. Mirrors, instruments, cameras have to stay cold, but we'll be constantly getting radiation from the sun. So the mirror part of the telescope up on the top has to be always shielded from the sun. And so those things that are folding out and being pulled out now are sun shields. So the sun will always be on the bottom side of the telescope from this perspective, and the mirror will always point out away from the sun. So this is a 5-layer sun shield. Each layer dissipates heat so that by the time you get up to the mirror part of the telescope, it will be very, very cold, around 35 Kelvin. So 5-layer sun shield, and then the mirror, again, of course, folds up kind of in 3 places so that it can fit inside the rocket, and then it will unfold after launch. And so that's part of what you're going to see now. That's the secondary mirror that just popped out, and then the final wings on the mirror come out last. Very complex engineering that's gone behind building this telescope. We've had to invent 10 brand new technologies in order to build this telescope. So it's been a long time in development and a long time in the works. But I'm a scientist, so I want to tell you a little bit now about the cool science we plan to do with Webb. So there are 4 main science themes. The first science theme, again, is we want to see those very first stars and galaxies that formed in the early universe. The second science theme is we want to see how galaxies assemble and grow over time. And then thirdly, we want to see how stars are born. And then fourth, we want to learn about exoplanets, or planets orbiting other stars outside of our own solar system. So the first science theme, the end of the Dark Ages, seeing the first light from the first galaxies. So again, back to our chart here of the history of the universe, we're missing that first kind of piece of the puzzle in galaxy evolution. Those very first galaxies that formed after the Big Bang. And with Webb, we'll be able to see those. So here again is the Hubble Ultra Deep Field, this time in a little bit of a different view. And here all the most distant galaxies that we found from this image are circled here. And what do you notice about them? They're all red, right? So the most distant galaxies we see are tiny and red. So if we want to see more distant galaxies, this gives you a clue that we need to look more red, which is what infrared light is. So that's why we need infrared light. So just last year, the most distant galaxy candidate yet has been discovered. And Hubble, as of 2009, or in the last servicing mission, has an infrared camera that sees very slightly into the infrared, into the near infrared. So with Hubble now, we have a little tiny bit of infrared that we can see. And with this little tiny bit, we've already seen some amazing things. And so this is a candidate of one of those most distant galaxies. And again, it's very red. And it's also very tiny, right? It's just a few pixels. So we can't see any detail about this. But with Webb, we'll be able to see these things routinely. We'll be able to see the structures and the details of these galaxies. And we'll be able, again, to answer those questions about that very first epoch of galaxy formation. So this is a computer simulation of how theoretical astrophysicists think things happen in the early universe. Of course, the early universe was much smaller. Galaxies interacted much more frequently back then. And in the very early part of the universe, we know that galaxies and stars, or stars within the galaxies, interacted frequently and underwent mergers. And so this is kind of a view showing how theorists think that happened in the very early universe. And those early galaxies are the ones that we can't see, that we want to see with Webb. So the second science theme is the assembly of galaxies, or how galaxies build up over time. And so now we're talking about looking basically back through all of the cosmos. So from those first galaxies all the way to nearby. And one of the things that we kind of have yet to really know a lot about, one of the open questions in astronomy, is how we go from those tiny, tiny clumpy things in the early universe to the large galaxies that we see today. And also, another big question kind of parallel to this is how black holes grow over time. So we know that all massive galaxies in the present-day universe have huge black holes at their centers, or something like 1 billion times the mass of the sun. But how they got that big is still an open question. And so we want to figure out how this galaxy assembly and this growth of black holes happens over time. Now we think one of the key processes of how this happened is galaxy merging. So this is another computer simulation that shows how two spiral galaxies, disk galaxies, much like our Milky Way, would interact if they came close enough to each other. So as you see here, what happens when these galaxies interact is the gas and dust inside them interacts gravitationally, pulls out these long tidal arms and bridges between the galaxies. And again, if both of these galaxies have black holes at their centers, they will eventually merge. And so we think that's one of the key ways that galaxies build up their mass and their black holes over time. So we think this is a key process in the overall evolution of the universe. But there are a lot of things about this that we don't yet know, and Webb is going to help us learn about that. So this is also snapshots from theory or from computer simulations of how we think this whole process happens. So two galaxies come together, interact gravitationally, and eventually merge. And again, we see this happening in snapshots in the universe. So these are real images from Hubble. Of course, these are 6 completely different galaxies. This process takes billions of years, so you could never see it in real time. But we can look at different galaxies that right now exist in these different stages. And from these, when we build up large samples of these, we can start to study a little bit about how this process happens. So the third science theme is the birth of stars and protoplanetary systems. So now we're talking about what happens within our own Milky Way galaxy, so closer to home. So again, I mentioned we know that stars are born inside dusty clouds, but we can't see them in optical light, which is what this is. But infrared light, which just came up, allows you to peer right through the dust and see the star inside being born. So this is another key reason why we need an infrared telescope in order to study this process of star formation. Of course, stars are a fundamental building block of our universe, and there's still a lot that we don't know about how they're formed. Again, we do know that they're formed inside these vast regions of gas and dust, and we can also model this. This is another computer simulation that shows how we think this happens. So we can study these regions inside, which when the gravity starts to take hold, that's when stars start to form. And so this happens, again, deep inside these dust clouds where it's hard to see in optical light. But infrared light allows us to peer in through the dust and see this happening. And so the fourth science theme, the last one, is planetary systems and the origins of life. And this is pretty far removed from my own area of research. I study galaxies. But for me, this is one of the most exciting. So right now, NASA currently has a really great telescope in space called Kepler. And Kepler has, to this day, detected over 1,000 planets orbiting other stars, or exoplanets. So we know that these planets exist. We know that they're out there. But there's a lot about them that we don't know. We know they're there. We don't know much about them. And this is, for example, an example of one of the stars that we know that has multiple planets around it. And of course, what we want to find is a planet that fits in that Goldilocks zone that might be able to host life. And so the Webb telescope, for example, would have the capability to detect water vapor in the atmospheres of these exoplanets. So you could start to think about the implications of what some of these discoveries might mean. We could be on the verge of discovering a planet that might have the capability of hosting life. And this is just another artist's conception of a recently discovered star that has multiple planets. We now think there are more planets than there are stars in the universe. So it's an amazing things that we've discovered already. And we have all these these detailed kind of science themes that we've developed. And this is how we build telescopes. We think up the biggest science questions of our day, and we build telescopes to answer those questions. And that's great. That's how science proceeds. But sometimes some of the most interesting things that we learn about the universe are the surprises, right? They're the answers to the questions that we didn't even think to ask when we're building the telescope. And so that's one of the things I'm most excited about this telescope, is to learn what surprises are out there that we haven't thought of yet. So we're building it. We've been building it for a long time. So I want to show you some of the images of the hardware that we're starting to assemble for this telescope. There are 18 mirror segments. This is down at Marshall Space Flight Center in Alabama, where we test the mirrors. So you see here, we test them in sets of 6, and all the mirrors are coated in gold. Gold is a really good reflector of infrared light. Very, very thin coating of gold. You hold it in your hand, kind of about the size of a golf ball over the whole mirror. So we coat the telescope, or we coat the mirrors in gold and then test them cryogenically. Of course, the telescope's going to be very cold, and so we have to test everything in very, very cold temperatures. Just another picture of the telescopes down in the chamber at Marshall. We now have all 18 of our mirror segments polished and coated in gold and cryogenically tested. So building the mirror segments is basically done. One of the hardest parts of this telescope, one of the hardest technologies, is finished. Here's one single mirror. A bunch of technicians looking in the bottom. I like this picture. This is actually up at Goddard. We have one of our test element mirrors in the huge clean room up at Goddard. And this was right when it first arrived, inspection of the mirrors. This is another mirror, not a primary mirror, the tertiary mirror on the telescope. And each of the mirrors, another one of the cool new technologies, each of the mirrors has a motor on the back called an actuator. And these motors allow each individual segment to move in 7 degrees of freedom. So it can rotate, it can tip and tilt, it can move in all sorts of directions, and it can even change its radius of curvature just a little bit. So that once we get the telescope into space, we can adjust all these little mirrors to make the telescope perfect. So we won't have a Hubble problem. We'll be able to have a perfect telescope once we get to space. This is the backplane structure of the telescope. So this is the large structure that all the mirror segments will fit on. This is out at Northrop Grumman in California. And one of the sun shields. So we're currently undergoing some crucial tests for the sun shields. This is what will hold the science instruments that fit on the back of the mirror. So this is also currently at Goddard, and this is flight hardware. This is what will be in space. We have 4 science instruments on Webb, and that will again allow us to see the universe in near-infrared to mid-infrared light. And so that is a summary of the telescope and of the engineering of the science. And I just want to point out that just like Hubble, this is your telescope too. Thanks.
Well, that is truly amazing. And I'm sure that we all have questions which we can entertain now. Yes?
I was wondering about the 10,000 planets that you identified. Are those in a particular zone or in a distance from us to the Big Bang, gathered in a zone, or are they all over the place?
So all of...
Could you repeat the question?
Oh, sure. So the question was, are the planets that we've observed so far, are they in a particular zone or a particular place? So there are kind of a few different ways to answer that question. The main thing is that they're all relatively close. So all the exoplanets that we've discovered are within our own Milky Way galaxy. So the planets are tiny. And the way we detect these planets is we look at a star and we watch for the light from the star to dip a little bit. And when we see that little dip, we know that something's passed in front of it. And so in order to see that tiny, tiny change of light, we have to look at things that are very close. So all the planets that have been discovered around stars that are pretty close to us, to the sun, relatively speaking. So they're all within our own Milky Way galaxy. And then the distance and the size of the planets, so the distance the planets are from their parent star and the sizes of the planets are all over the place. Again, because of the way we detect them, a lot of the exoplanets that have been discovered are huge planets, very close to their star. So think like Jupiter orbiting where Mercury orbits. And that's, again, just because that system produces a larger dip in light, so they're easier to find. But we've discovered planets that are roughly the size of Earth, maybe a factor of 2 bigger than Earth, and so they're kind of all along the spectrum. And we've discovered lots of planets, or lots of stars with multiple planets too. But all the ones we've discovered are close to home, so to speak.
So I'd like to ask how the Webb telescope compares to projects that have been canceled, like the Terrestrial Planet Finder. So I don't think the Webb was originally developed as an exoplanet research device. So how much of the gap will it be able to fill in? I mean, will it be able to do spectroscopic analysis, for example, of planetary surfaces? And how much of that can you really achieve with an infrared mirror?
Okay, so the question was, will Webb be able to kind of fill in the gap in exoplanet science, and be able to do spectroscopy in infrared specifically? And the answer is yes, it will. So we have several very high-tech spectrographs on Webb. One of the brand new technologies that we developed is the main spectrograph on Webb is it's a micro shutter. So we have an array of tens of thousands of tiny little shutters that we can open and close, and that will allow us to get spectra. So it's really just a very advanced way to do spectroscopy. So it turns out that a lot of the signatures that we might want to detect in exoplanet atmospheres do fall in the infrared. So like water vapor, methane, some of these key signatures of life do fall in the infrared. And so we will definitely be able to, I think, make large leaps forward in exoplanet science.
How far, with the Hubble telescope, we're able to look at almost the beginning of just past the dark ages. How much have we seen of the prototypical galaxy at that edge, and how much more do you think we'll be able to see with the Webb telescope in terms of just what the galaxies look like at the birth, right after the dark ages of the Big Bang?
Okay, so the question is, how much have we been able to see kind of at the edge of what we can see with Hubble, and what more we'll be able to see with Webb? Did I get that right?
Yeah, the prototypical galaxy.
Right, the prototypical galaxy that existed in the early universe. So the answer is these most distant galaxies. For example, the plot or the image I showed where the little red galaxies were circled in green. Those most distant ones that we've seen, that's it. That's what we can see. They're tiny red dots. In many cases, they're only a few pixels. So we can detect them, but we can't see the details of them. And so that's what we need Webb to see. Again, I'd mentioned that a larger mirror helps us to see finer detail, and of course a larger mirror helps us to collect more light. So with Webb, we will be able to literally open up that era in the early universe and see those galaxies in detail. We'll be able to see structural properties of those first galaxies. So right now, what are only tiny blips on the screen, essentially, we'll be able to see those in detail. We'll be able to see structures, see what they look like, if maybe they look like they're merger remnants, something with these tidal tails and all those things. We'll be able to tell more details about them, like how many stars they're forming. So Webb is going to allow us not only to see them, but to study them in detail, again with spectroscopy. So, getting a spectra of a galaxy is like getting the galaxy's fingerprint. And it tells you a lot about the chemical properties of what's happening, in the physical properties of what's happening in those galaxies. And right now it's just impossible. We can't do that on those early galaxies, but with Webb we'll be able to do that.
Since you have multiple cameras, why not have a visible light camera?
So the question was, since we have multiple cameras, why don't we have a visible light camera? And so the short answer, I think, is because we have to, in order to build the telescope in a reasonable way, and within the budgets and within the time scale, we have to limit ourselves. And so, again, driven by the science, we decided that infrared was the way to go for this telescope. Now, Webb will have a tiny little bit of visible capability, so kind of red light. Webb will be able to see. So the red light that Hubble sees, Webb will be able to see. But in order to optimize the way the telescope will work in infrared, for example, the gold coating on the mirrors is because it's an infrared telescope. So we kind of have to focus on that one part of the electromagnetic spectrum. Now, of course, we're already starting to think about what might come after Webb, way down the line, and one of the thoughts is that the next kind of big thing after Webb would be a large optical or UV telescope in space. But that's all very, very much in the works.
Amber, I wanted to get your opinion on an interesting statement I heard from a talk by Lawrence Krauss, a theoretical physicist. He said that as time goes on, the universe will be expanding at a faster rate, and at some point, he said 5 billion years in the future, we actually won't be able to detect anything outside of our own galaxy because the other galaxies will be expanding faster than the speed of light. Could you comment on that? Does that speak to the urgency of today's space exploration?
Sure. So the question was based on some recent comments from Lawrence Krauss, who is also at Arizona State University, who he had said that the universe is accelerating in its expansion, and so something like 5 billion years from now, we won't even be able to see other galaxies. And so does that give us a sense of urgency in as far as advancing this kind of technology? And yeah, that's absolutely true. So the discovery of dark energy, the Nobel Prize that was awarded just last year, that's what dark energy is. It's when astronomers don't know what something really is, they call it dark, right? So dark matter, no idea what it is. Dark energy, have no idea what it is, but we know that it's there. And it's this dark energy that's driving the acceleration of the universe. So we've known for a long time, again, Hubble discovered, Edwin Hubble, a long time ago, that the universe was expanding. So we've known for a long time that the universe is expanding. But it's only recently, in the last 15 years or so, that we've begun to discover that not only is it expanding, but it's accelerating in its expansion. So it's expanding faster and faster all the time. And so this does mean that in 5 billion years or so, we won't even be able to see other galaxies. So we're kind of in a great point in history, right? Because we can look out now and see the stars and see the galaxies because of where we happen to be in the point in the evolution of our universe. So yeah, we have to build these things. We have to build them now. I probably won't be around in 5 billion years, but yeah. But I mean, definitely, in all seriousness, I think that these big, bold projects like this, like Webb, and like our space exploration that NASA does, these are the things that make our country great, right? These are the awesome things that really, I think, propel humanity forward. And so I think that investment in these kind of things is absolutely essential in order to keep us moving forward, I mean, as a species even, to keep us moving forward technologically.
But there was one other person right behind that gentleman who had his hand up when he did.
There's already at least one space telescope that's designated to infrared spectrum. How much more sensitive will the Webb be compared to the existing infrared telescope?
Okay, so the question was, or the comment was, that there's already an infrared telescope in space, and how much more sensitive will Webb be? And so the answer is yes. NASA has a great infrared telescope right now that's orbiting the Earth, the Spitzer Space Telescope, and it is comparatively a tiny telescope. Its mirror is like this big. It's kind of less than a meter. So it's a small telescope. It also sees the universe primarily right now in near infrared. So it had a couple of instruments that had to be cryogenically cooled. Again, right, an infrared telescope has to be fairly cold. And that close to Earth, the Earth warms it up. So a couple of the cryogenics part of Spitzer have ceased to operate, and so part of the capability has been taken away because of that. But the answer is yes. Spitzer has done really great things for astronomy. Even with this tiny little, relatively speaking, workhorse telescope, infrared telescope, we've been able to learn a lot about the universe. But of course, Webb is so much bigger, and the capability, the technology development between when Spitzer was launched and when Webb will be launched has been, it's huge. The difference in the detector technology and the difference in really just all the technologies that have gone into building Webb are going to mean Webb will be hundreds of times more capable than Spitzer.
gentleman in the back row.
I'm just curious. You said that these two galaxies, they have a collision somewhere, right? And that each galaxy has a black hole at its center. And I was just curious. You know, I watch a lot of this Stargate stuff. That is there a connection between that if I fall into this black hole, that I come out in this other galaxy, or can you pinpoint coordinates? Is there any kind of research in that area? Astronomy.
All right, so the question is, when we have these big galaxy mergers, what's going on with the black holes, and questions about falling into black holes, and a lot of this stuff. And yeah, there are some great programs on TV about this. And the physics of black holes is crazy. I mean, basically, once you get inside a black hole, the singularity, physics breaks down. We don't know what happens inside the black holes. And the prospect of falling inside a black hole, of course, one would hope that would never happen. But if you were to get close to a black hole, all sorts of crazy kind of things start to happen. Like time starts to seem different. Time starts to slow down, and you start to see things kind of, further away, move more slowly. All kinds of crazy physics goes on around black holes. But to bring it back to the galaxy mergers, we do think that process of two galaxies merging together is one of the key. So again, black holes that exist at the center of galaxies are huge, like 1 billion times the mass of the sun. But they obviously weren't that big at the beginning of the universe. And so we have to figure out how they got that big. And we think that galaxy mergers, that's one of the ways that might have happened.
Next, we'll have the gentleman in plaid who had raised his hand. Had you not? No? Yes.
I just had a quick question on the lifespan of a web.
Okay, how long will Webb last? That's a good question. We are in NASA speak, the formal science requirements are for 5 years, but we're carrying enough fuel to last for 10, 11 years. So depending on the efficiency of the launch, however much fuel we have left, we'll keep using it to point the telescope and to keep the telescope in its orbit. So we're hoping for like a 10, 11 year mission.
Have you, has NASA selected the initial targets that Webb's going to be looking at?
That's a great question. I was actually just asked that yesterday by someone else. No, not officially. There are a lot of, I'm sure there are lots of astronomers across the world that have great ideas about where to point this telescope first. And I have my own great ideas. But I don't think that's been decided yet. I feel pretty certain that those deep fields will be one of the first and most exciting targets that Webb will point at. Because, again, we see so much, right? There are 10,000 galaxies in that tiny little piece of sky. And, you can just leave to the imagination what Webb will see there. So I think those deep fields will be something very exciting. And also, between now and launch will be 2018, we'll keep discovering these exoplanet candidates. So if we happen to find an exoplanet candidate that looks like it might be in that Goldilocks zone, right, that would be an obvious, really exciting target for Webb.
And one more question from the gentleman in the second row, and then we can...
What are the prospects for servicing the telescope? Will we be able to do anything to it once it's out there?
So the question is, what are the prospects for servicing Webb? Yeah, so I kind of started out my talk talking about how we've been back to Hubble 5 times. But Hubble and the space station, for that matter, are exceptions to the rule, right? We build, or the aerospace industry builds satellites to not be serviceable, right? To work on their own once they're launched. And, the satellites we depend on every day for our phones and for our direct TV, for all of those things, GPS, all of those depend on satellites that are not serviceable. So Hubble's really an exception to the rule. So we've used all of this knowledge from the aerospace industry about how to build satellites to build this telescope. So the answer is it won't be serviceable. It'll be too far away. It'll be 1 million miles away. And we don't currently have the capability to get 1 million miles from Earth with humans. Robotic servicing might be an option later on, much later on, but we are building the telescope to work like it's supposed to once it gets to its final orbit. And that's one of the reasons we still have several years to launch. We've actually built a lot of the telescope. As I had mentioned, the mirrors the mirror segments are basically finished. You know, we've come so long in actually inventing the technologies, first of all, and actually building the hardware, that these last 6 years or so are going to be used to assemble the telescope, of course, put it together and test it. We have a very, very rigorous test program to make sure that every little subsystem and then every bigger system and then the whole telescope works like it's supposed to once it gets to space. So we won't be able to service it, but we're building it such that we won't need to.
I'm going to break the rules that I just said, and I'm going to introduce a question because she keeps mentioning new technologies invented for the telescope, and I wondered if she would like to comment on that, and then we'll end our formal question and answer session, and you can approach.
Okay, so the question was about new technologies invented for Webb. So to build these big, kind of bold, cutting-edge things, we do have to invent new technologies. And I've already mentioned a couple of the technologies that we had to invent. Those mirror segments are made out of beryllium, which is number 4 on the periodic table. Beryllium is a very toxic element, and so we have to be very careful in how we handle it and how we make it into its mirror. And so the mirror segments are, again, made out of beryllium and coated with gold. And the technology, by making a segmented, deployable mirror is difficult. And so that's one of the first things we had to do, was just figure out how to build a telescope that would be deployable. And of course, Northrop Grumman, again, is our prime contractor, and they're the experts on building deployable optics and deployable systems in space. So we're confident that we've got that down. And the mirrors are the motors that are on the back of the mirror segments that I mentioned. There's lots of new technologies that have gone into building those, and even some of the elements used in those mirrors are kind of cutting-edge technologies on using different kinds of magnets, different kinds of things in those mirrors. And then the micro shutter array, which I already mentioned as well, was built at Goddard, and it's an amazing instrument where if you go, well, I've been to several. I observe with Hubble, but I also observe with ground-based telescopes here on Earth. And so when you go to a ground-based telescope and you want to, for example, take spectra of galaxies, what we do is we have literally metal sheets, and you cut slits in them to place over the galaxy. So, right, you have a slit over a galaxy, you get a spectrum of the galaxy. Okay, so that's how we do spectra here on Earth. Obviously, we can't cut metal plates and send them up to Webb, so we had to invent this micro shutter array, which again is thousands and thousands of tiny little doors that you can magnetically open and close to act as the slits, so that you can get the spectra of these galaxies. So yeah, those are just a few examples. There are a total of 10 technologies that we had to completely invent in order to build this telescope. And again, this has never been done before, right? You have to build this thing in 1G and in Earth temperature to work in zero gravity in a cryogenic environment. So it's very hard, but we've made so many advances in the technology such that we have a really great telescope in the works, and really excited about the science it will do.
Thank you very much. Thank you.